What is the displacement field and why do we care? So imagine I have a charge right there, a free charge. I'm going to call it a free charge, and I put it near an insulator. Well, the electric field from that free charge is going to polarize insulating material, and now I have charges in there that I have to consider their electric field. So if I want to find the electric field at some place, maybe right there, it's the sum of the electric field due to the free charge and those polarized charges. So we can describe that material with the polarization vector P, which tells us how those charges are separated, but it depends on usually, not always, the applied field. Okay, well, that's fine. Now we can use this special identity that says the divergence of the polarization is the charge density over epsilon naught, the negative. And so you can imagine that if this is a changing polarization region, then you would have charges closer to each other and you'd have a charge density. We call that a bound charge. Free charges, bound charges are charges that are grouped together. The net charge for the bound charge density is 0 because they're all due to dipoles. So we can split that up. Now, if I use Gauss's law, the divergence of the electric field is the charge density divided by epsilon naught. That's just Gauss's law. And then I separate my charges into free and bound charges. And then I use this bound charge up here. That should be a bound charge. I can write the divergence of E is this divergence of the polarization over epsilon naught negative and the free charges. And then I just move that to the other side and pull out the gradient. I get this epsilon naught, and I multiplied by epsilon naught. Epsilon naught times electric field plus the polarization vector is equal to the free charge density. And so we call this term inside the displacement field. It's the thing that's like the electric field. It's not the electric field. It's like the electric field that includes the material, right? We're trying to incorporate what happens to the material without having to calculate all that stuff. We're not trying to find the electric field. We're just trying to find what happens, and that's the displacement field. So it's easier to kind of calculate the displacement field in a region where you have some insulator, and then you can find the electric field later.